Okay, good morning. The other day in class, I had to go to a meeting, so I wasn't able to walk you through how to do these mega complex problems. But I wanted to show you, you do every single problem the same way. And although these are more complex, they're not necessarily harder. They just got more parts to them. You have to be careful. So let me do another example. In the last example we did in class, we had two blocks joined by a cable being pulled by a horizontal force. And the cable in between creates a tension, and the tension is always equal. So in this example, we have a similar situation. We have a mass 1 connected via a cable over a pulley to a mass 2, and this is one continuous cable. So we can say there's tension in this cable created by this hanging mass. When this system's initially at rest, when I let go of it, the M2 is going to be pulled down. That's going to fall. This block's going to start moving. The whole system will accelerate. The key to these problems is make sure when you draw your free body diagram, do a free body diagram for each object and don't go outside the free body diagram. What I mean by that is when you're looking at M1, a lot of people, what they do is they sort of put a dash box around M1 and you only look at M1. So you don't look, when you're doing the free body diagram for M1, don't look outside that red box. There's a tendency to see this cable to the right and think, oh, it's being pulled down here by M2, which it is. But since we don't really know or care what's at the end of that cable, we just call it tension. So there are shortcuts that sometimes work, but the method I'm going to show you always works, and it always works the same way. So let me walk you through how to do this. I'm going to draw my free body diagram for M1, like we did the other day. I know there's a tension pulling it to the right. Obviously, there's a friction problem, so we're going to have friction pulling it to the left. Because it's on a horizontal surface and I don't have any weird components of applied force, I know that I have a FW, which is mg, m1g, and I have my normal force pulling back. Obviously, this object is going to be accelerating to the right. So again, I don't want to include that as a force on the diagram, but I want to acknowledge the fact that it's moving to the right and accelerating to the right. So I can write a free body diagram just like we did before. I can write an equation just like we did before. Because it's Newton's second law, I have F net equals ma. I always like to remember that it's m1a. Be careful with the subscripts. Don't forget which match you're working with. The net force in this case, the T exceeds the friction, so it's going to be T minus friction equals m1a. And we do what we did before. We solve for T. And in most of these problems, you're going to have two unknowns in each equation, tension and acceleration. That's usually what the problems are set up. Because we have two unknowns, we need to get two equations. So this is equation 1 plus, and FF will be mu m1g. You can derive that out, but by now this should be relatively obvious. If not, we'll review this next week, don't worry. Now I'm going to look at M2, so I'm going to do the exact same process. M2 is being pulled down by M2g, or by its weight. It's being held up by that unknown tension. Just like the block on the horizontal surface, it's going to accelerate because they're joined together. They have to accelerate the same. Hey. Okay, sorry, brief interruption there. I think we're back. So again, these two things have to have the same acceleration. There's no way one can accelerate one rate and the other rate because they're joined by a cable. So again, for the second object, we're doing the exact same thing. We're going to only just look inside the, I usually dash this, but we're only going to look inside the box when we draw our free body diagram. So we have weight pulling down, we have tension pulling up. Again, it's going to be accelerating down. So now I know there's a net force. So I know I have a net force, F net equals M2A. I don't know why that's doing that, but that's okay. M2A. So the net force again will be M2G minus tension equals M2A. So again, we have two unknowns. We're going to solve for tension. Tension can be M2G. I'm bringing T over and bringing that back over, minus M2A. And now I can set these two equations equal to each other. So I'm going to set that equal to that and solve for A. And the trick to that is just getting both terms with A on the same side and then factor out the A. Vicky Flam. So again, just work your way through carefully through these. Just make sure you have subscripts on everything. If you leave out a subscript, you're going to end up doing some algebra wrong. So just be careful of that. And again, I will be back in class on Tuesday. Monday I'm out, unfortunately. Tuesday I'll be back, and we'll have a lot of time to go over a bunch of these. You're at the point now where there's virtually no problem you can't do. So you'll see some mega death problems coming up soon.